Oh yeah, the ones. Okay, great. Um, so hi guys. I'm going to talk about what can we do with physics. So a bit of some applications of physics that you might or might not have heard of. I think at least one you heard of. So we'll start with exactly these four topics. Then at the end, I'll do a quick recap and I'll tell you why I think it's good to have this in perspective. So we'll start with rotations, and everything starts in 1687 when Newton publishes his most famous work. He actually publishes this work and it contains like all of his motion laws, the universal gravitation law. I hope all of you know that what that is. Um, but there's something really um, particular and that I'm sure you might have not heard of that it says, which is that the free surface of a rotating liquid forms a circular parabola. Okay, fancy words, but what this means is that if you have a bucket of water, for example, the surface, as you rotate the bucket, just forms a circular parabola, which is basically a 3D equivalent of a parabola. Um, and something interesting is that Newton was the first person to manage to build a telescope using mirrors. So he used like a spherical mirror because it looks like a parabola and a parabola is a great mirror and light rays come directly every single them is to have a focused image. But Newton didn't think about two ideas. It was only in 1850 that introduces the idea of a liquid mirror telescope, which is that if you actually manage to achieve a stable rotation, which means a stable circular paraboloid, and that liquid acts like a mirror, maybe we can build a liquid mirror telescope. Thing is, in 1850, we didn't actually manage to create such stable rotations. So the paraboloid would be very wobbly and we can get a proper focus in one image. But as things progressed in 1982, after a lot of technological advancements, I think you might guess that between 1850 and 1982, we've had various technological advancements. Emmanuel Bora, I think, starts working on modern liquid mirror telescopes. Like this one, this is NASA's liquid mirror telescope. And basically, it's just a very big cylinder with liquid mercury inside, which is like a metal that's liquid at room temperature. And as you rotate that disk, and it forms a circular parabola, and it's able to watch the sky that's directly above. Now, it's only able to watch the sky that's directly above it, but to build compared to normal telescopes. So if you only need to watch certain stars, maybe it's a good idea to build one of these because the quality image is also going to be very, very satisfactory. And it all starts with our friend Galileo when he published a dialogue concerning the two chief world systems. They're debating about whether geocentrism and heliocentrism is the best system. Um, but I'm not going to talk about that. I'm going to talk about what they said about of the pendulum, one can impart considerable motion. So this is a lot. I'm going to try to explain it. Basically, if you have a pendulum, um, and you just knock it a little, it starts oscillating with like super tiny angle. But let's say it oscillates with 2 oscillations per second. If you like get a baseball bat and whack the pendulum, it might start like getting some very, very big angles, but it will also oscillate at 2 oscillations per second. So each pendulum, each of these harmonic oscillators, as we call them, has something called the natural frequency associated with it, and it depends on the material and the length and whatever. Um, so Galileo said that if you actually manage to blast it with a certain frequency, which is the same of the natural frequency of that pendulum, you can actually make it move uh, impart a considerable motion in the pendulum independently with how much force you actually blast it. So to formalize things a bit better, in 1750, Euler derives and solves the equations of the undamped simple harmonic oscillator under forced oscillations. What does this mean? This means that he figured out mathematically how those pendulums work when you actually force those blasts Galileo was talking about. And he came to a really interesting conclusion, which was that among all these cases, the one which deserves particular attention is that for each 2b equals a, which I'll explain in a minute, in which the oscillation distance eventually grows up to infinity. Now, 2b equals a in this context is referring to the frequency of our forced oscillations and the natural frequency of the pendulum. So if they match, the oscillation distance of the pendulum will eventually grow to be infinite. So how does this relate to bridges? In 1826, John Fitzgerald, a very, very wealthy man, funds the construction of this suspension bridge, the Broughton Suspension Bridge. And then 5 years later, in 1831, the 60th Royal Rifle Corps crosses the bridge under his son's command, actually, because he was a lieutenant at the time. So they were doing a military exercise and they marched through there. And as they were marching, their steps became synchronized and it matched the natural frequency of the wobbling of the bridge. So 30 seconds later, the bridge ended up collapsing. Now, um, no one actually cared about the natural frequency of the bridge at the time. It didn't spark much attention because no one really knew how to describe it at the time. There were a lot of theories, but now we know that it might have been that because in 1940 there was another much bigger incident in Tacoma Narrows, the Tacoma Narrows Bridge, um, in in which basically we have this really really gigantic bridge, like concrete bridge, but on a certain day, strong winds were blowing, and I'll let you watch what happened. So really weird. Now, this is hard concrete. I promise this isn't like any special type of rubber that they decided to build bridges with. It's just that along with various other physical phenomena, um, the winds managed to hit the bridge and actually accompany its natural frequency. So as Euler said, those oscillations would eventually go up to infinite, and the bridge started wobbling. So eventually came crashing down, and the world actually started thinking about resonant frequencies or natural frequencies when they started building bridges. So now moving on to general relativity, which I think you might know better than bridges. Um, It all started with Einstein in 1905. He publishes a paper in electrodynamics, and he introduces special relativity there. Then he realizes that clocks tick slower at higher speeds. I hope you all know that after this camp, and I hope I'm not bringing any traumas back. And then in 1915, sorry to bother you with Einstein again, he introduces the theory of general relativity now in a paper of its own, and he says clocks tick faster in weaker gravitational speeds. Fields, sorry. There are no such thing as gravitational speeds, I think. So I'm going to talk now about Sputnik 1, which was the first man-made satellite to go to space. And in 1957, the Soviet Union launched it, and then two scientists at the Applied Physics Laboratory in the Johns Hopkins University can pinpoint its location using the Doppler effect, which means like they measured the time light took to get there from the satellite, and they can pinpoint it. And this led to a really really interesting idea, which was, can we do it backwards? Which means, can we use a satellite to actually pinpoint our location? And the answer is yes, we can. And in 1973, the Pentagon actually creates the Defense Navigation Satellite System that was later called NASA GPS. And in 1983, after an incident, which was a civilian, a commercial flight, actually accidentally flew over Soviet airspace and it got shot down. So the US president at the time, Ronald Reagan, declares that the GPS will gradually be made available for civilian use, and now we all use it in not so much as in a daily basis, but we use it very frequently. So we know that special relativity tells us that the satellites are going faster than us, so they end up losing 7 microseconds per day. But general relativity says that they are in a weaker gravitational field, so their clocks spin faster and gain 45 microseconds per day, which means that if you add it up, they gain 38 microseconds per day. And just to give you a perspective on the effect, we're here on that white dot, which I can point out for you there. We're there, and if the GPS, if we actually tracked our locations with the GPS that didn't have general relativity into account, we were here at the beginning of the camp, and then afterwards we would be somewhere along this circle. So we could be visiting Aveiro and having some really nice off malls. I don't know if you've tried them, but they're really good. Or we could have done the Santiago de Compostela pilgrimage and go a bit northern to the Spanish coast and maybe catch some sun up there. I don't know. I would have liked to get some sun there if somebody wants to join. So now going on to radioactive decay. It all starts with Miguel. Sorry, Hector, if I'm butchering your friends.
That's okay.
And he started looking for a connection between phosphorescent materials, which included some uranium salts, and the newly discovered X-rays. Now, phosphorescent materials are those kinds of materials that absorb light and then emit it, like those emergency plants that we have on our dorms. They absorb light and then emit it at night. The boys are looking at me because I know they've used it to do some fun drawings, I guess. And then how he did it was that he got some photographic plates, covered them in black paper so that no visible light can go through, and then put them outside with some phosphorescent materials, like pointing towards them. So his idea was, I'm going to get these phosphorescent materials to emit light and then try to detect X-rays because the visible white light will be blocked by the black paper. But one day it was overcast in Paris, so no sun, a lot of clouds, and he left all of this stuff locked away in a cabinet. And he thought to himself, well, maybe I could develop the photos either way. And to his shock, the developed photos were as distinct as the ones who had been in the sun. So this could only lead to a single conclusion, which was that uranium actually does not need an external source of energy to emit radiation. It emits radiation on its own. Then 2 years later, Marie and Pierre Curie published a paper acknowledging that other materials and not only uranium can emit this radiation, and they named it radioactivity. Now, let's go talk a bit about something that has nothing to do with radioactivity for now. I'm going to talk to you about the two types of random numbers that we can generate. You'll get why in a minute. Now, we have pseudo-random numbers, which are algorithm-generated numbers, that actually seem to be random, and we can do statistical tests to confirm that they seem to be random, but are actually determined by these equations. So we can actually figure them out if we know what the equations are. So they are deterministic. And those algorithms are faster and more convenient than the other method I'm going to talk about, but obviously they are predictable. So they're used like in certain simulations, in sometimes scientific simulations, for example, need to take into account random factors. So we can use these numbers for that. Or we have lower security cryptography or encryption and etc. And there's another method, which is uh, true random number generators. And true random numbers are numbers that are generated by certain physical events. To give you an example, Cloudflare generates random numbers by arranging a bunch of lava lamps, and then it tracks down where each bubble in each lava lamp is, and it pops out a random number. So this is a true random number generator because you can't really figure out where everything is going to be at the same time. But this one is kind of a lie because you can actually figure out if you compute every single equation of motion of those lava lamps where the bubbles will be. But either way, these methods are slower and less convenient. Of course, I don't think we have like 50 lava lamps lying around at our homes. But they are truly unpredictable. And they're, of course, very useful for higher security purposes. Um, and as quantum physics evolved after Marie and Pierre Curie ended up discovering radioactivity, we actually found out that radioactive decay is a stochastic process. Now, so stochastic is a really fancy word that just means random, so don't worry about it. And although we know that if we have like a bunch of radioactive atoms, we can know when half of them, for example, will decay. That's called an half-life. For example, if I have 500 radioactive atoms and their half-life is like 10 years, we know that after 10 years, only 250 of those 500 atoms would have decayed, and then another 10 years, and out of those 250, we would only have 125, and so on and so forth. So we cannot predict with precision, or we cannot predict at all when a single atom is going to decay, because that's impossible. Radioactive decay is random. So in 1956, these two Japanese scientists, which I am not going to try to pronounce their names, published an article in a kind of a magazine uh, explaining how they built a true random number generator using radioactive decay. So basically, they just got a device which only function is to count how many atoms have decayed in like 10 seconds or 1 second or whatever, it depends on what you want. And they know that number is random because they know quantum physics. So as they count how many atoms it's decayed at a time, it can pop out random numbers because number is obviously random. So this came up with a whole subsection of true random number generators, which are quantum random number generators. Now there's a bunch of them. There's one's based on quantum tunneling, and another's based on optical quantum effects, which I'm not sure how they work. But there are actually a ton of those. And Well, now, um, from the 2000s to here, they have been in development and they are being commercialized by private companies for various uses. You can use it for very high security purposes or just in an online casino because sometimes people like to play the roulette and the roulette needs random numbers. And if you figure out the algorithm for a roulette, you doom the casino because you're always winning. So casinos don't want to lose money. So going up on why this matters, I'll give you a quick recap. We had rotations in 1687, and then a technological advance, which was the liquid mirror telescopes in 1982. This is the top view of a liquid mirror telescope, by the way. This one is in India, I think. It's the ILMT, yeah, which is in India. Then we started with oscillations in 1632. That's a double pendulum. It's a really fun thing to see live. Um, and ended up with an upgrade in bridge construction only in 1940. And then we had general relativity in the beginning of the 20th century and ended up with GPS systems in 1973. And lastly, I talked about radioactive decay, which was kind of discovered in 1896. And then we ended up with quantum random number generators in 1956. Now, why did I want to talk about all of these random things and why am I putting all of this into perspective? I firstly want to talk about something that people always say, which is when I'm talking with someone about what I study and what I want to do with my future, it goes something like, oh, I really like general relativity, or I really like astrophysics. So maybe I want to do something with that. And almost like 90% of the time, their answer is, oh, so what can you do with that? Okay, this is very frustrating. And to me, I don't like this idea that science needs to actually be practically useful all the times. I don't think it should impact our daily life all the times because, as we've seen, rotations started being like understood by Newton in 1687, and then 300 years later, we created liquid mirror telescopes with a simple conclusion that we made. And for example, radioactive decay was discovered, and then we developed random number generators out of it. So it's kind of all like a big snowball. Science generates science, and as science generates that science, we evolve as a species because we become more intelligent. And if we become more intelligent, it also becomes much easier for us to develop new science. So it's kind of like a butterfly effect. You always end up with some sort of of a new scientific discovery, which will actually be practically useful for us. So much like a butterfly can generate a tornado simply by clapping its wings, um, I think we should look at science as the butterfly and not as the tornado, because for scientific development to actually have an impact in our lives, we should start thinking first. If we don't start thinking first about whatever makes us happy, we're getting nowhere, and nobody gets nowhere. So I just want to assure you, and I want to pass this clear message, which is um, do something that makes you feel happy, not something that you think is going to make other people happy. Because by doing something that makes you happy, you'll be generating science, and you'll be generating better science because there's a lot of passion into it. And the the odds are, in my view, that you'll probably have a greater impact in the world in one way or another. So that's my presentation. I hope